Welcome to the July 2024 indoor meeting of the Raleigh Astronomy Club. Before we get started, I want to go over a few safety procedures for us. Look around for room hazards. Make sure, because we got the kids with the summer camp and stuff all over the place. We've got cables behind the projector, chairs with bags next to them, the lights down low. Naveen's fully bearded. Do I have anybody who's CPR trained? Okay, you're up. Who's my emergency caller? Who's got a cell phone and dial 911 in case of a problem? Susan. Okay, fire equipment is on the back side of under the clock, basically. That doesn't. Yeah, that's a good idea. So for those of you on the phone, please be aware of your surroundings and let any of us know, let anybody else know if you have a problem. So safety routes, go out this door. There's an emergency exit that way or that way. You'd probably be better off to go this way and go up the stairs and go out the locked doors that way and that way. Okay, we want to keep everybody safe so we can wave at you at the next get together, please. I like the one in the back. Go, Marshall. Okay, if you're a first-time guest or this is a new club member, please see us, walk up to us. We sometimes are busy talking to other people, but we want to hear from you, okay? Members on Zoom, please say something to us when in chat. Let us know if you're a new member. Do you want to hold questions to the end or interrupt? Absolutely. Okay, so we're going to wait till the end for questions, okay? And when you ask a question, it needs to go in here. There you go. So, or in the chat window. Let's go over our upcoming events. Maybe? Yes. So we have First Fridays coming up on the 2nd. We have the Willard coming up on the 7th. Art Space on the 17th. First Fridays again on the 6th of September. And the Willard again. And then November, we got Morrisville Community Library. Okay, so tonight, after we get done, if you want to go socialize some, we're going to go to the Alamo. That seemed to be the vote that I took this week, that a lot of people wanted to go to that. So we'll go again. Tonight's presentation is, I can read this without my glasses on. No. Mike is a scientist in the Laboratory Studies Group at the Jet Propulsion Laboratory at California Institute of Technology. He obtained his PhD in organic chemistry and worked in the pharmaceutical industry for 20 years. He changed his career in 2012 to planetary science and astrobiology. Good choice. His current research program combines laboratory experimentation, spacecraft remote sensing, planetary mapping, field geology to explore planetary processes, particularly dissolution geology on Saturn's moon Titan, the astrobiology of deep glacier ice microhabitats. He was the deputy principal investigator of the multi-institution NASA Astrobiology Institute node investigating the possibility of life on Titan, as well as the project scientist for the proposed Oceanus. Yeah, there you go. Titan orbiter mission concept. He has performed field work in an extremophobe sulfide cave in southern Mexico and drilling into the Greenland ice sheet at Summit Station, Greenland. Thank you for making that super difficult for a redneck from North Carolina. So I give it to you. You have to hit.
I think I did. Did I hit it? Can y'all hear me okay?
No. You're good. No, you're good.
Nope, I think it's good.
Stop.
Am I good? Okay, good. Okay, so quick. Thank you guys for inviting me out to speak with y'all. Quick show of hands. How many of you guys think that we're going to find life, that there is life on Mars? Show of hands. Even like after yesterday's events, this is it? Wow. Okay, you guys are tough. Okay. How many of y'all think that we're going to find life on Europa? Okay, we're doing a little better. How many of you guys think that we're going to find life on Saturn's moon Enceladus? Wow, you guys are a tough crowd. Okay, I got it. How many of you guys think we're going to find life on Titan, Saturn's moon Titan? Okay, we're doing pretty good. Okay, that was about maybe 30% of the crowd. Good. So I don't have too much stuff to try to do to win you over. Good. So we're going to try to talk about some of the geology of Titan, and then we're going to go right at the end and talk about the astrobiology, but I can talk about that forever. So if you have a lot of questions, I'm all yours. Okay, so we're going to start off with a little tour of Titan. One of the things we do, let me try click. Yeah, click. I'm just going to advance it. Okay. Try this. Is that working? Okay, cool. Okay, so here's some really quick, fast facts between Earth and Titan. So both places have an atmosphere. Titan's atmosphere is actually really thick. So Earth's is only a puny little 100 kilometers high. Titan's is about 1,000 kilometers high. When we were planning the Oceanus Titan orbiter, we had to be up about 1,000, 1,500 kilometers above the surface. Otherwise, atmospheric drag would spiral us in. So we were way up there. So it's a very low gravity environment. So the atmosphere is really distended out. You guys remember hearing about the 7 minutes of terror for landing on Mars? Because it's a really thin atmosphere. On Titan, it's referred to as 90 minutes of boredom. When you try to land on Titan, when they landed the Huygens probe, they actually had to cut the chute and add a smaller chute because otherwise it would have taken just too long to land. So Titan has a great atmosphere, which makes it really easy to land big stuff on Titan. So for exploration, that's just awesome. Pressure on Earth is about 1 atmosphere. Yeah. On Titan, it's about 1.5. So it's an even thicker atmosphere than we have here on Earth. The big difference is the temperature. So on Earth, we're right about, 25-ish, Celsius. So it's decent, nice temperature. Titan, it's about 95 Kelvin. It's so cold that we use the Kelvin scale. So that's about maybe 20 degrees above liquid boiling nitrogen. When you see science demos, that's 77. Titan is just a little bit warmer than that. So it's really, really cold. What that means is that air temperature combined with the cold makes it really dense. So walking around on Titan would be the equivalent of kind of fighting your way through a down pillow, which means if you want to fly on Titan, you could go into your garage, build yourself a set of wings, and you could fly under your own power on Titan because you have thick atmosphere, thick, dense atmosphere, and very low gravity. So it's really cool. Okay. On Earth, we have a liquid cycle, whether we have rain like we have yesterday. Titan, there's methane rain. It's liquid hydrocarbons, but very small ones. Our rock on Earth is silicates. Crustal rock is also luminosilicates. Titan, it's organics. And then underneath that, you have water ice, which everybody likes to say it's about as hard as rock. It's actually more like soft rock, maybe more like gypsum. It's not super, super, super hard. Okay, but you would say that from all these differences, that Earth and Titan are going to be really, really different, weird places. But what we're going to start looking at is we're going to see that they are very, very similar, but you have very different conditions on both. So it's really a great way to learn about the fundamentals of geology and how geology works on other worlds. Okay, so what makes Titan Titan? So this is a shot that kind of sort of what we would have seen from Voyager. This is actually a Cassini image, but you're looking across the haze deck of Titan. Titan is this incredible organic factory. You have all these beautiful haze layers. You can't really see the surface, which is a bummer, but you have all these molecules being made in the upper atmosphere. You have methane, sunlight hits the methane, breaks it apart, makes new molecules, and it just goes wild. Here is an example of what they used to think Saturn's, Moon, Titan's atmosphere used to do. This little complicated diagram was done pre-Cassini. It's really simple compared to what we know now. Currently, we think there's like about 400 simultaneous equations all happening, and we know already that that's an oversimplification as well. Titan is like the most complicated, awesome chemical experiment ever. And we could learn so much if we could take a probe, send it through the atmosphere, upper atmosphere, learn about all this chemistry. It would basically start a whole new science of planetary organic chemistry. So what happens is that those molecules all react, they make things. Eventually they make little polymers, little solid materials. They start to descend through the atmosphere. They get bigger, they get larger, they glom together, they stick, and eventually they go down and they end up on the surface. How much of that goes down there? A lot. It turns out it's a very, very large amount. When we talk about Mars, people get really excited if they have like a little sniff of methane, and maybe they might have a little trace of organics that they detect. On Titan, we think there's like hundreds of meters of organics, like huge amounts. And that's like maybe after about 1 billion years of production. Titan's been around for like 4 billion years. So we're seeing some places, I may be able to show you, I don't think I do in this slide. We have some places where we think there's like a full kilometer thick of organics. Think of like the Grand Canyon and all those beautiful layers. All of it is organic molecules like hydrogen cyanide, acetylene, benzene, weird things called tholin, all sorts of stuff. Titan is an organic chemist's paradise. Okay. Right. So why is that kind of cool? So it turns out that one of the things that you can do in the laboratory is you can take a little bit of nitrogen, a little bit of methane, add some light, add some energy, a little bit of electrical spark discharge or something like that. And you get these weird things depositing and coating up the flasks. Kind of like when you cook and burn sugar or something, you get this gooky stuff in the side of your pot. You get this stuff. And this is the kind of stuff that we think is being made in the upper atmosphere of Titan. These weird like orangey blobs, these black blobs. But what's interesting is if you take this stuff, you put it in water, you boil it up with a little bit of acid, a little bit of base, you end up making amino acids. And amino acids, we know if you couple those together, you can start building up peptides, which can become functional proteins. So you might actually end up having a lot of the precursors of life sitting there right there on the surface. In fact, one of the things, a paper that came out was suggesting that adenine, one of the DNA bases, is made directly in the atmosphere of Titan. No processing, it just naturally comes together and falls out right there on the surface. It doesn't have the sugar or the phosphate backbone, but it's, you know, you've got some of the pieces and parts right there. We think that Earth may have gone through sort of a Titan phase very, very early on when it was just starting out, so that when we go and we look at some of these molecules on the surface, we might be seeing what Earth might have looked like before it got reacted with water, and then what may have eventually turned into us. So when you look at this molecule, this weird yellow stuff, you might actually be looking at your great grandfather when way back when, right? So learning about Titan will teach us a lot about Earth and what may have started off in the before chemistry turned into biology. Okay, so that's pretty much what we knew about Titan after the Voyager flybys. We had these ideas of molecules. We had these ideas of lab experiments. Unfortunately, we wanted to see the surface of Titan, and this is kind of what we saw. It was like a big fuzzy blob. Couldn't see the surface. We had no idea about the geology. And then we had the Cassini mission, and this is when things changed. So this is a picture of the Cassini spacecraft as it's coming into the Saturn system. It's doing its retro burn, and it's going to park itself in Saturn system. It's going to orbit around, fly by Titan from time to time, actually use Titan to change its orbit. And if you look there, right at the bottom of the spacecraft, there's that kind of like that little dish-looking thing. That's going to be a probe that they're going to send down to the surface of Titan. And we're going to get a really good close-up look and maybe even like kind of a taste of what's down there. So here's one of the first pictures that we got of Cassini, from Cassini of Titan itself. And what this is an infrared image that's used to be able to penetrate through that haze and through all that methane. Special wavelength is about 0.93 micron. And so this is the first full view we have of the globe of Titan. And there's a lot of stuff that we got going on here. It's really cool. This is just an amazing image for a lot of reasons. One of them is that you notice that Titan is not uniformly coated in stuff. There's dark stuff and there's bright stuff. So that means that all that stuff coming down onto the surface is not piling up like snow. There's something that's able to geologically turn it into dark stuff and bright stuff. That's cool. So that means Titan's got something going on. The other thing is you start looking at you guys do observations. You look at the moon, you look at Mercury, you look at Mars, you see craters, right? You see other worlds, asteroids, you see craters, moons of Saturn, craters. You look at Titan and you don't see craters. You know that it's out there, it's being hit and pummeled with different things all the time. So that means that there is some type of a process that's able to remove those obvious craters on Titan's surface. So Titan has something going on. You look at Earth, and we also have a few craters, but not a lot because Earth has a lot of geology going on. So this is telling us that, Titan's differentiating. It's different. It's got some processing going on. It's got some geology. And then in this picture, look down there at the bottom of the South Pole. You see those little white spots? Those are clouds. So those are storm clouds, not just haze. That's actual clouds. So Titan has weather. And we learn later that it actually floods and rains on Titan. There's rivers and lakes. So it's got a lot of stuff going on. So right now, you've got an image that this is something really cool. Okay, I'm going to switch from using infrared because it's not super great. I like to be using radar. I was part of the Cassini radar team. And the way that radar works is you shoot a longer wavelength signal down to the surface. And if there's lots of rough, scattery, blockety blocks, you'll get that radar signal back and it'll look very, very bright. If it's something that's really smooth, like a floor, a carpet, or muds, or sand, you'll send the radar beam down and it'll just kind of scatter away and you won't get that signal back. So it'll look dark. So if it's bright, rough. If it's dark, smooth. So over here, I have a picture of the Mojave Desert in California. All right. Okay, you see that little line right there? That's actually a highway. That's actually I-40. So if you guys ran out here and took I-40 out quite a ways to California, you would end up in that area. So this is in Mojave National Scenic Area. That's Kelso Dunes way up there. That's a nice big dune field. And if you look down in the radar image, it's really dark. It's because it's really smooth sands. But those mountains are all kind of crinkly because then that gives you a nice bright radar signature. Looking at radar images, for me, the best way to think of it is you're looking at aluminum foil and you're kind of lighting it up from the side. So stuff that looks crinkly is mountains, and stuff that looks dark and smooth is basically dark and smooth sands. Okay, so when we first started looking at Titan, these were some of the images that we saw on the equator. So these are incredibly long, huge dune fields. You do have a weird effect here with the radar, is that because the radar angle perfectly matched the face of the dune, you effectively reflected and got a perfect reflection back at you. So all those little lines where you see the bright spot, that's the forefront part of the dune field with respect to the radar. And then the little dark line behind it is kind of like the downrange, darker part of the dune patch, the other part of the hill. You see these huge, huge dunes. This is extending for hundreds of kilometers in this scene. Those dunes are hundreds of meters high, and these effectively wrap almost around the entire world. And those dunes are made out of organic materials. So you've got a huge amount of organics that you see right here in this image. And you see this kind of like this bright, patchy white stuff. Those are kind of like icy bits kind of sticking up out of the dune field. One thing that we saw is that when we look, we can see these little bright white, these bright patches of mountains that are kind of poking up out of the dune field. And you notice that these lines kind of go around those bright spots and they reconverge down on the backside. If we look over here at Earth, we can see the same thing in the dune fields of Earth in some of the deserts. And this is in Egypt. And we can see these dunes that kind of diverge and go around these dark mountains poking up, and then they recombine on the backside. Now, what's really cool is that both of these images are at the exact same scale, and they're behaving exactly the same. Look at the dune spacing, look at the way they converge, look at the size of the mountains, everything matches. All right, so you've got totally different dune materials, totally different gravity field, different temperature, different pressure, yet everything is behaving the exact same. So just in this image, you just figured out something really important about geology, that dunes, and when they diverge and come around obstacles, it's a very universal thing. You can kind of predict the spacing. So if we went to another planet and we had like argon dunes or something, you would predict that if they're diverging around some sort of an object, they'll probably have the same spacing, and they'll probably have the same way that they converge and go around. So we just learned something really fundamental about geology and how dunes work. Cool. So one of the things that we started to do is try to look at all the radar images, look at the other spectral images, microwave emissivity, which you can get off the radar data as well. And we were trying to kind of inventory and map the surface of Titan to figure out what's actually down there. This is myself, PI Rosalie Lopez. This is Tiffany Verlander, who was an intern. This is Ashley Schoenfeld, who was an intern, became a grad student, became a doctor in planetary science, and is now a postdoc at JPL. So very talented group of people. And this is us trying to start doing this mapping of Titan. And the way that we did it is we first started with taking all the collected radar data and kind of building a radar stack, kind of like what y'all do when you're doing your observations. We have issues because the data is really crappy at Titan just because of the way things work. You have different incidence angles with the radar. You have sometimes radar gaps where you don't have it because, you know, Cassini was a flyby mission, so it did what it could. And so you sometimes have to combine it with infrared, which can sometimes be very, very, very different data. We stack everything up, and the first thing we do is we start trying to draw lines to say this over here is different than this over here. Sort of like we call it drawing the contacts. And then once we do that, we turn the contacts into like a polygon. We try to kind of classify them out, and then we draw the surface features on top of it. So in this case, we have a very large crater. This is about 400 kilometers across. We'll get into that in a second, why that's important. And we define the outer rim, we define some of the interior bits, and then we found the apron, and lo and behold, we saw some fluvial stream channels on the side of that as well. So when we do all of this, we created the first map of an area around Afakan crater. Oh, right, yeah. So there's Afakan right there in the center, and we defined these different units as purple is sort of the dune units, green is what we call plains, and then the red is kind of a crater, and then you have these little mountain units that are orangish yellow. Maybe not showing up so great here. If I can add as well the Dragonfly mission, the relocatable lander is going to be landing just south of that crater right there. That's called Salt Crater, and that's the Dragonfly target. They're not going to be actually going very far on Titan. There's going to be a lot of stuff that's going to be still unexplored. So we drew all of this up, and we did it around the entire globe, and we basically did an inventory of, you know, what is Titan? Oh, good God. Wow. I'm really sorry about this. So, hold on. Okay, it does not look like that on the screen. I'm not sure quite what is happening, but yeah, so, right, so we have dunes are sort of this horrible brown color here. The plains are this kind of light blue color, and we've mapped some lakes up in the poles. Let me get away from this. Sorry, hopefully this doesn't project. Yeah. All right. They do actually. Yeah, they look great. Like, oh, that looks good. And like, ooh, gosh. Okay. Well, are they projecting okay on the Zoom? Okay, fine. All right. Sorry for y'all who you get the benefit of being in person. So okay. Um, so here we've taken a lot of the mapping that we showed you before with the different swaths, and I've colorized it to show the organic stuff. So we didn't know exactly how much of Titan that we were looking at was icy and how much of it was organic. In the very, very earliest mapping, they did some wacky, wild interpretations and they said, oh, everything is ice. Later on, we looked at the data and figured out that, you know what, it's mostly organics. And you can kind of get the idea, at least looking from this screen, that there's a lot of green being shown. And that is true. So most of Titan's surface is covered in organics. There's a few patches of ice, and that's kind of in blue in this image. And there's a few things in yellow that are hard to see where we're not quite sure. But the overall theme and the takeaway from this slide is that most of Titan's surface is covered in organics, possibly quite thick. We did some mapping to isolate the dunes. Oh, good, this came out a little bit better. So everything that's in purple is now the dune fields. We looked in detail at the dunes to try to, and this is a clue that's kind of we noticed on Titan as well, is it's very latitudinally stratified, which is kind of a story. So you have dune fields in the equatorial zone, you have plains in the mid latitudes, and then you have lakes way up at the poles. So that's telling you that whatever is driving Titan geology or these different types of units must be somehow related to weather, which is kind of cool. So when we started looking in detail at the dunes, we looked at how the little lines and how things tapered and trying to figure out the way direction, the way materials moved. And we were able to figure out the wind pattern for most of Titan. And you have to kind of look at this in detail, but what we saw was that in the equatorial zone, stuff is moving from the equator into the plains, and stuff is moving from the high latitudes down into the plains as well. So when we were looking at the dunes, we said, oh, on Earth, that must be where all the stuff collects. And that's actually wrong. It turns out all the stuff is collecting down in the mid latitudes. So you're like a little dune particle, however you turned into a dune particle. Eventually, you're going to end up in the mid latitude deposition belts at about 45 or 35 north or south. And that's why we don't see a lot of mountains in that area, because they're basically all buried. So we're getting this idea of a lot of organics and how the sediments move around on the surface of Titan. So that's a really cool thing. Another wild thing is that when we were looking at some of these patterns, we noticed that they didn't change very much from local topography, which is weird, right? You always have winds on Earth, which, if you're like in a valley, the winds go whipping through the valley. That's not happening on Titan. There's a much larger global scale that's happening, at least when the materials are moving. What we think happens, and this is really wild, is that we think that Titan has really big convective storms from time to time. And those convective storms get so big that they shoot up into the upper layers of the atmosphere. Titan's atmosphere is structured very much like us. It's just scaled. And it overshoots and it brings down upper atmosphere winds all the way down to the surface. You guys might remember the movie, The Day After Tomorrow, where there's the guys flying around the helicopter, like, oh my God, we have a stratospheric hole, and then all the helicopters go shooting and drop down. So we think that actually happens on Titan for real. It doesn't happen everywhere. We think it's like a little patch here and a little patch here, but over enough time, the eons, you get this overprinting of upper atmosphere winds down there on the surface. So the day-to-day of the dunes, they're probably not moving around at all. But you have that once every 1,000, 10,000 year event when it just howls. And then that's when these stratospheric winds get brought down to the surface in this one area and print this pattern on the surface. So we put together kind of like a quick story in the dunes where you have materials coming down from the upper atmosphere, being maybe washed into playa basins, and then those get picked up, turned into dunes, wind transport, shoosh on down, and eventually they end up in the mid-latitude plains. We also see mountains down there as well, little crinkly things. Here's the mountains of Titan, and I'm going to compare it with some of the little bit higher resolution radar data coming from the Himalayas. We also think that we have a cryovolcano on Titan. So it's effectively like a volcano here on Earth, but on Earth, volcanoes erupt molten rock. On Titan, they're going to erupt molten ice, which you and I both know as water. So your drinking water glass is effectively Titan lava. And so when you look at this, you have this big mountain construct and you have like this deep slit that's almost like a full kilometer down. It's huge. And we think it extended out and flowed out kind of into the distance. And we think that might be very similar to the Laki volcanic region. I have a picture of that in Iceland. Okay, so those are the pictures that we saw from the mid-latitudes and the plains. When we got to the poles, this is where things got really wild and interesting. And we saw this, right? And this looks like a lake. And that's exactly what it is. And it's like, oh, okay, I got it. Wow, it's a lake. And everything looks kind of normal. You see islands, you see seashores, you see rivers, and everything looks normal until you start looking close. And I want to point out these two rivers down at the bottom here. You see how they're kind of flowing parallel? That's kind of cool. They're flowing parallel, so there's like maybe a ridge or something in between them. They flow along, and then they kind of approach the shore of the lake, and they just keep on going right beside the lake. Earth rivers don't do that. Earth rivers, they like to flow into a lake because that's the lowest part of the lake. This is kind of going along and it just ignores that lake. It doesn't care. Okay, look what happens to it later on. It comes along and it intersects this other river that goes across it. And then it keeps on going and then it crosses another river, kind of like a hash mark thing, right? Earth rivers don't do that either. They don't intersect like an intersection on a road. They merge and then they join and then they flow downstream. So there's something really weird about the way that Titan rivers work. We think that on Earth, most of the rivers are driven by topography. Rivers flow downhill. That kind of probably happens on Titan too, except there might be more control from the structure of the bedrock. Maybe there's like cracks or joints in it. And then the liquids are flowing and following the cracks and the joints wherever they go. And as long as it's kind of oriented with the topography and elevation, it'll follow that joint. And so that may make it follow a joint that goes right along the boundary of a lake, so it doesn't care. And then maybe, if the lake floods, it'll cover up the river. If the lake pulls back, then it'll reveal the river again. So this is telling us now that Titan rivers, there's going to be similar to Earth, but they might be a little bit different in how things work as well. Okay, these lakes, by the way, they're huge. So this is Ligeia Mare. It's bigger than the largest lake on our world. There's one even bigger that's about 300,000 square kilometers. So that's, bigger than all the Great Lakes combined. We don't have oceans on Titan, but we do have seas. Most of the time, Titan is pretty boring, but every now and then we'll have what we call almost like this global spasm where it'll just erupt. And we had a cloud monitoring campaign with the Cassini spacecraft looking at Titan, seeing how the weather, and it was boring. And then all of a sudden, boom, there was this one day where everything just lit up. And for a moment, Titan actually looked a lot like Earth, where it had kind of like an intertropical convergence zone, and then kind of like storms coming off and spiraling around in the mid-latitudes. We think Titan has a single Hadley cell where you have heating at one pole, and then that air rises and then descends in the other pole. But right around the equator, you have the Hadley cell starts to switch, and you now effectively have two Hadley cells, and then you'll have this eruptive spasm of storms. We think this might be the time when those big stratospheric winds might actually come down to the surface, is during the equator time. So for the most of the time, Titan is very boring, not much going on, but around the equator, or around the equinox, really wild stuff can happen, and it can be localized as well. So the next few days after this, clouds went away, everything went back to boring. We have channels on Titan. So here is the ejecta apron of that Minerva crater. We have these beautiful channels that kind of flow. It's actually a whole story right here. It's you have these channels. You don't see a lot of meandering. So it's just kind of like swishing, swashing, very much like a glacial outwash. what is cool, there's a couple cool things in the images. One is you can see these channels coming out. They all come together into this embayed region out here. We think a lot of this is actually exposed water ice. And then what you notice is you look way over there in the upper right, you're seeing these little dunes starting to build up, these linear dark patches and streaking away. So now we're getting an idea that, there's probably like a lot of sand grains around here. They're being washed together into this bay, collected, and then eventually the winds kick in and start moving. So we're getting now a picture of the sediment. Another thing is if you look right here at where some of these arrows are, these are dunes that are kind of sand deposits coming out of a crater. And what you notice is as that dark patch, kind of streaks across, you can look that right where those bright channels are, they kind of pinch out. On Earth, where you have water, flowing water, rivers, and dunes, usually the rivers truncate the dunes because it washes the sand away and it keeps the wind from taking the dune away. Opposite thing is happening on Titan. It looks like Titan, the dunes are more powerful than the rivers. And so when there's a dune approaching a river, it actually affects and it pinches out the river a little bit. So that means when we're thinking about different processes, on Titan, wind dominates rainfall. On Earth, rainfall dominates over wind. Cool. So we're getting an idea of how different processes work. Here's a picture as well of something that we had discovered. That's a meandering channel. That's a big one, really big. I think I can make it blink. Yeah, I can make it blink. Okay, so that's the radar image, and you can see this beautiful meandering channel. That is the scale. This river on Titan is the same size, scale, and pattern match as part of the Mississippi. So this means that the fourth largest river in our solar system is located on Saturn's moon Titan. It is not flowing with water. It is flowing with liquid methane. That substrate that you see there is all organic, so it's swooshing its way through an organic substrate. Unlike the other channel that we saw that was whooshing through ice sediments, this one is actually got some really big incised meanders in it. And meanders are typically the type of thing you see when you have cohesive sediment. So this is telling us that that sediment is kind of sticky. And the thing that's really cool is notice that it's an almost perfect match in the pattern. So we never really understood what makes rivers meander. That's sort of still a mystery. We can simulate it in like little fluvial beds or little fake things and scale it up, but we never actually understood what the physics are behind it. Well, now we have an example on Titan where we have different liquid, different gravity, different pressure, different temperature, different viscosities, and yet it's meandering the exact same way. Perfect match. Maybe a little bit wider because of lower gravity, but overall, we've just discovered something very fundamental about how liquids behave too. So when we do go to another planet and we discover this liquid argon river, and if it's going through a cohesive sediment, I will tell you that it'll probably meander just the same way as this. Same scale, and it'll be perfect match. We just learned something fundamental there too. Okay, so we can put together kind of like a big cycle of how things, you've probably seen this sort of diagram in earth science books where we have, rainfall and then rivers. So on Titan, we think it's a little bit different. You have these atmospheric chemistry products coming down, and then you have rainfall hitting it. You have outwash, evaporation, a big cycle. One of the differences, though, is you might have dissolution happening as well. Maybe you have caves happening on Titan. And that was one of the things that we started to investigate. Hopefully this stays. So here's an image of what we call an area that has a lot of dissolution geology. So that big, huge river that I showed you a picture of before, Mississippi size, that's over there in the corner. So you can get an idea of the scale of this thing. We showed this image to a professor who specializes in dissolution geology on Earth. It's called karst, like limestone areas. And he looked at this as, you basically have a textbook example of everything that I want to show in a textbook to talk about how dissolution geology works on karst. So it's perfect, but it's on Titan. So we have places that are these huge plateau that are highly, highly dissected. I've kind of drawn a picture here so you can get an idea of how to interpret our radar data. But you have these big, deep, wide slot canyons, really big scale. We have this empty lake kind of thing here, but if you look carefully, you notice that the river channels all go away from the lake. So it's actually not a lake. It's actually what's called a polye, which is sort of like a temporary ponding basin in dissolution geology. So everything here is matching that it's basically matching up with what we know of on Earth dissolution geology. The difference here is that some of these plateaux are about 500 meters thick, and we know that they're made out of organic sediments. And then a really big thing is that we know that from looking at other terrains, these are really old. So what that tells us is that when Titan's organic chemistry turned on, it probably turned on right at the very beginning of Titan, and it has not stopped. It's been just cranking out molecules to build up those big, thick sediment layers. So there's a lot of organics on the surface. We did a lot of work in a laboratory. This is me. This is actually a laboratory setup that we use for simulating a lot of ocean worlds at JPL. All the Titan work is done kind of in that back chamber. We have the advantage of we use nasty stuff, but it's also at normal room pressure, and we just have to cool it down to the right temperature. So we work with a lot of liquid nitrogen. And what we did is we're able to make a little bath with a beaker, and inside that beaker, we can simulate a Titan lake. We can hold about the right temperature, and we can play with liquid methane. And liquid methane is really fun to play with, by the way, very splashy. And what I'm going to show you here is a picture of how dissolution geology works on Earth. You start with a big block of something that can dissolve, like limestone or salt. You hit it with rainfall, it starts to get little pits. Those pits start to grow. And as they grow, they kind of start to coalesce. And eventually you start to dissolve everything away. And all you have left is a couple of little mountains left. And when we start looking at Titan, we see exactly the same features. So here's a picture. I'm actually going to compare it. Some of the stuff that we see on Earth. This is what's called polygonal karst in Papua New Guinea. And we have an image here from radar of Titan. And what's really cool is if you look carefully, you can kind of see that there's like a definite orientation of the walls on Titan. Titan is actually a better analog for karst than some of the stuff that we have on Earth for textbooks. If we had a little bit better data, just a little bit, we would probably have some really good pictures to talk to teach geology. Okay, here is another picture in Guangxi province in China. Some of these places where you see those tall mountains, those are actually dissolved away. So it's the remnants of what didn't dissolve in China. And you can see that they're all kind of like oriented up. You can see a river channel way in the back there, but you don't see very many other rivers because everything's kind of percolating into the subsurface and going underground. We look at Titan, we see almost the exact same thing, same sort of orientation of these valleys. And then you can see over there, there's a very hint of kind of like a cliff face that would be sort of like a river of about the same size in relation to the hills. One of the things I'll point out, and this is a big mystery that we're trying to figure out, is that everything that has to do with dissolution on Titan seems to be 10 times bigger than its corresponding features on Earth. And we don't know why. We saw like with sand dunes and with rivers, everything seems to scale really good. For karst, it doesn't scale. For some reason on Titan, everything's much bigger. If there was karst on Titan and it was similar to Earth, we would not have seen it with our radar. We didn't have the resolution. So something is able to make these features much, much bigger. Here's an example of a series of different valleys and plateaus, which kind of shows how these things evolve. You have these joints, which seem to be set spacing. And then as they get older, they become wider and wider. And so you can have like a natural evolution sequence of Naraj Labyrinth is very young, Saikan Labyrinth is about middle-aged, and then way at the very end, you have the Two-Pile Labyrinth, which is basically just a bunch of remnant ridges. And the next stage that's going to happen is eventually those ridges are going to go away and you'll have a corrosion plain. One thing that all of this karst stuff is telling us is that there's some type of an uplift that is happening. And this is getting exciting and starting to track into astrobiology because we're suggesting that you have water coming up deep under the ice, hitting a brittle ductile transition zone deep underneath about maybe 30 kilometers. And then that's pushing up these big plateaux. But this water is going to be fairly warm, maybe coming from the deep subsurface ocean on Titan. And this may be actually a habitable environment down there. You have a place where you might have organic molecules mixing in, and you might have some water mixing in, and it's kind of warm and toasty, and the pressures and the temperatures match the conditions at the base of the Greenland ice sheet, and we know that there's microbes that can survive down there just fine. So we now think that there's at least deep Titan might be a fairly habitable environment, and the question is, how do we figure that out? Okay, so going back to labyrinth terrain, here's an area in Western Australia called Pernalulu. We think this might be an excellent analog for Titan, where it's not like pure block of limestone. It's actually got a mixture of silica and other stuff. And all you need to do to make dissolution terrain is just weaken the bonds to allow stuff to flow and get transported out of there. So you have these remnant ridges, and then you have these plains of materials that have been eroded away and kind of swept along and downwashed. So this might actually be a really good analog of Titan. Studying this place, we might be able to figure out a lot of stuff. Okay, so we can put together an overall geology story from what we've got from orbital images. We have atmospheric photochemistry, surface deposits, stuff being moved around by rivers, stuff being moved around by wind. It gets thrown into a basin. Eventually, some of that basin can get uplifted, and now we have these labyrinths. That can now start eroding again and start moving around the sediments all over again. So basically, Titan is a sedimentary world, maybe even more so than Mars. Okay, so that was everything we learned from orbit. But we did have that lander, the Huygens probe, and we landed on the surface of Titan. And this is some of the first images that we saw when we came out of that haze. They're not super awesome, but they're precious. And one of the things you can see is you can see these river channels. And you see the ones over here on the right are very, leaf-like, dendritic. They all come together. That's a typical kind of thing you would see from overland flow. Over here on the left, you see these straight, short, stubby little linear river networks. That's the kind of thing you would see from dissolution, where you have subsurface percolating in, and then it kind of releases all of a sudden, and you make like a river channel from that. All of this scene basically would only be 1 or 2 pixels in radar. So we now know that when you get closer to Titan, you're going to see a much more rich, geologically fantastic landscape than what we've even seen from radar. We also know that the surface of Titan now, from this image, can vary just on the order of a few kilometers. You went from somewhere where you have subsurface geology to another place where you have surface geology with the rivers. Amazing stuff. And there's a lot of mysteries in there that we don't actually know. I'm working on a mapping project right now to try to figure out what the geological history is of that. Oof, so sorry. Okay, so here is an image. Maybe I can like turn it so you guys can see it. So sorry. This is the image of what Huygens saw when it landed. And it saw like a very orange foreground. And you saw a bunch of these rounded cobbles. And rounded rocks on Earth are formed from erosion, from clacking together. And we think the same thing might have happened as well on Titan. You had everything kind of banging around together and kind of round these cobbles out. You also can notice that all the cobbles are about the same size. And that's a clue that as stream, flood, whatever was washing these cobbles and depositing them, it carried everything that was about the same size, and then it lost energy so that it couldn't carry that particular size anymore, and then it dropped them out. So it's sorted, which is really neat, which means that, okay, there was probably a lot of stuff going on. It probably moved quite a bit of material, and it lost energy here and dropped the cobbles here. What we don't know is we don't know what those cobbles were made out of. If you read the Wikipedia article, they'll say there's water ice. If you read the scientific literature, there's actually really no evidence that they're water ice. If you held, if you really forced me to answer, I'd say, yeah, it's probably water ice, but it could be acetylene, it could be benzene. I have no idea. The data is not good enough to be able to tell. So that means that we have this really cool image, a really cool geological story, but we actually don't know what the stuff is actually made out of. Okay, so I'm going to kind of start to wrap it up and give you kind of like an idea of the scorecard of Earth geology versus Titan geology. Both Earth and Titan have very few craters. They both have dunes, both got mountains. Titan may have cryovolcanoes. clouds and storms, active weather, lakes, rivers, changing features, absolutely on both of them. So Titan is a very, very Earth-like world. The one thing that we don't know is we don't know about life. Is there life on Titan? We know we have all those organics. We know those organics can now get down into the deep ocean. What we think might occur is that you might have some way of getting stuff down there. And we actually have an idea. Remember that crater that we saw we were mapping maybe 400 kilometers across? We think that crater was so big that whatever made it, that impact punched all the way through 100 kilometers thick of ice and mixed in with the ocean. So we did some modeling. We published on that 2 years ago. So at least we have one instance where we breached all the way through and probably actually dredged up ocean material onto the surface of Titan. That is a great astrobiology target, by the way. So we think that we got stuff injected down in there, all those organics. Bacteria love eating organics. So they may have eaten the organics, may have lived in some of these locations where you had, some ice injection underneath these labyrinth terrains that lifted up. All we would need to do would be to go do a deep drill mission down into Titan and start looking for things. We want to do this on Europa. We want to do it on Enceladus. Titan might be a really good place to go look as well. Okay, so future Titan exploration. There's been a lot of concepts that have been proposed. One has been selected. Some of the things that are really nice about Titan is you have, thick air, you have liquids, and it's perfect for flight. So we had an aviator airplane that was proposed, or actually was kind of fought through as a possible proposal. Titan balloon, the time Lake floater actually went all the way to step 2 in discovery. And then most recently, the Dragonfly, which is a relocatable lander, has been selected for flight. And I think that's launching in 2028 under the New Frontiers program. So we will be going back to Titan. And the next thing that's on the list is going to be the potential for a Titan orbiter. So with that, I'd like to kind of thank you all for inviting me out here and letting me talk to you to death about Titan, because I love it. And I'm more than happy to answer any questions from in the room or online that you all might have. So thank you very much.
Notice your names at the bottom.
Yes. So I was the concept artist for the Aviator aircraft.
Thank you. Appreciate your enthusiasm. A couple of questions. I forget my high school chemistry, but you used the term organic in what sense? You said, I think I understood that sand is organic.
Yeah. So when we're referring to organics, we're using the term to mean it would be something that would have maybe like a carbon-carbon or a carbon-hydrogen bond. And if you had to say, Mike, what do you think those sands are actually made out of? It's probably a mixture of a lot of things. But there's been some work that suggests that it's maybe acetylene, which can convert over to benzene, which can convert to phenylacetylene, and then maybe naphthalene, and maybe phenanthrene. So I can start whipping out and drawing structures of what it might look like.
Okay, you mentioned that there's frozen water on the surface. Why no oxygen in the atmosphere in this, what you put up there?
Right. Okay. So that's a really good question. So there's really no good. It's a very reducing atmosphere. So yeah. So we think that in the before time, Titan kind of assembled itself from collective cometary bits that came together. And then there was probably a melting event that partially differentiated out Titan. So a lot of the heavier stuff ended up going into the core, but it didn't totally segregate out like it did on Earth. So it's probably like a bunch of lumpity bump stuff down in the core. The water kind of came out of it, and probably some of the organics, such as you find in cometary material, may have actually gotten fairly cooked and turned into ammonia, or turned into methane, which percolated up through the crust, came up into an atmosphere, or extruded and mixed into the water. And then from the conditions, we think that the ammonia may have converted over to nitrogen, that gives you your nitrogen atmosphere, and the methane may have percolated up and then gotten blasted by sunlight, which then gave you your organic molecules. So there was never a point where you had a lot of free oxygen, probably not even a lot of carbonates either. So it's probably a very reducing environment.
couple more questions. You described a river. Any guess as to how fast they flow?
No, that is an excellent question. I'm trying to remember. I think that there had been somebody who had done some work and suggested that it might be very similar to Earth rivers as well. Although, let me pull back a little bit. We think that a lot of these rivers might be dry and transient. So like in the American Southwest, when you have a big, huge rainstorm, you have stuff come together, you can get what's called a hyperconcentrated flow. If you guys ever watch like some of those YouTube videos where there's a big flash flood and you see like all these rocks and stuff just banging together, and it's just, you have so much of that stuff in there tumbling around, it actually changes the density of the river. So it can be a little bit slower than, I guess, if it was just pure water, but it's really powerful and it does a lot of geological work all at once. Yeah, Frank. Oh, yes.
Are these pictures you see right there actual images of Titan with the grouse or planes superimposed on there?
No, those are not. Those are all faked images. I'm trying to remember where they all came from. So the image, actually, wait, you know what? Let me take it back. I think the ESA image of the Titan balloon, that may be part of the Huygens image in the background. The image of the floater is, I think that's completely fake, done by Mike Carroll. And I think the image of Dragonfly, this is an earlier image, was done by Mike Carroll. This one was done by me, taken out of the window of an airplane. And I did a lot of Photoshop on it. But this back here is I-8, and that is Blythe, California in the back. I think those are the old woman mountains, if I recall.
Otherwise, they could simply take an actual image and then computer superimpose the grouse onto that.
We actually don't have any images that are that good of the surface of Titan. The best resolution we have for radar is about 200 meters per pixel. It's really, really not great.
And by the way, Titan is the second largest moon in the solar system, followed just behind Ganymede, and our Earth is at number 5.
Okay, so you know that they used to think that Titan was bigger, but they figured out that it was mostly atmosphere that they were seeing. So it kind of lost its status to Ganymede. Yes.
So Mike, I was kind of curious, what is driving the thermal activity on Titan? Do you guys know much about the core? Is there a magnetic field? Is there any indication that there's tectonic activity of any type?
So it's a little bit complicated, the story of Titan. What's the thermal history of Titan? So it probably came together, radioactive decay. So we think that for a long period of time, about 3 billion years or so, Titan probably looked very different than it does now. We think it probably looked a lot like a thin crust Europa. You had a very large ocean. You had ocean directly in contact with the core. You probably had very thin ice, craters punching all through all the time, probably a buildup of organics on top of that. We think that maybe about 1 billion years ago, which is fairly recent, we think something changed in the thermal history and it started to cool down a lot. And so you had a thickening of the ice shell, you had a buildup of high pressure ice down at the base. As the ice built up, it probably changed the whole isostatic properties of the crust. And you may have actually, it's weird, but you may have actually shrunk, tightened a little bit because you had this high pressure ice, which is actually denser than regular ice. And the whole thing kind of shrunk and you got like these fold belt mountains. A lot of the mountains are very linear and then they run east-west, which is weird. And so we think that the mountains and maybe these labyrinth terrains all formed kind of about the same time, but only about 1 billion years ago. And then if you had gone back to maybe like 2 billion years ago or beyond, it probably looked like Europa, but with like really, really thick layer of organics on top of it. So it's kind of cool. So we're actually looking at Titan at a fairly recent surface, which could also explain why you don't see a lot of the craters, because they may have formed and sloshed all the way through. And so the early cratering history was basically erased because it just was never there. Yeah.
Okay, my question. I had trouble understanding the rivers over the lake thing with the hashtagging. Is that like a visual almost similar to like that freshwater river that runs under a saltwater ocean that's in Mexico?
Oh, I see. Okay. So I don't think that example, let me go all the way back to that picture. If we want to talk about the lakes, there's a lot of really wacky stuff going on in the lakes that we don't understand at all. But for this particular lake, so you're asking if there may have been like a denser fluid that was kind of flowing down through the lake. And that might actually happen. So there's a lot of really weird things that can go on with the Titan lakes. I've given you kind of like the overall version that, oh, it's just, methane stuff. It's actually methane with a lot of nitrogen dissolved in it. There's also another liquid that can happen, which is ethane as well. And so there's also propane. So there's actually a couple liquids going on Titan, and they all have like kind of different density profiles, and they may actually not always mix well. If you mix them, they won't separate, but you may be able to layer them very gently and get them to behave differently. So getting to your question is like, could there be like sort of a river that comes into a lake and it maintains its shape as it goes shooting through the river? That is possible. I think that if I understand it correctly, that it's assumed that the rivers that are coming from rainfall are probably methane rich. So they're going to be a little bit lighter. And that might actually be the exact opposite which happening is where as the methane goes into the lake may actually have a little bit heavier mixture of a little bit of ethane. And so it actually makes the methane kind of skim across the surface of the lake. And it actually, instead of carving out a deep channel, it actually ends up making a lot of these lakes really shallow. But there could be, but you know what? That's just this one lake, and it could be others where what you were talking about does the same thing. There's a lot of wackiness with Titan lakes. And you also have cases where we think the liquids might be going from one pole to the other. So there could be periods where the lake is totally dry. And so you have a carving of valleys much deeper into the lake. And then when the lake liquids come back, it starts recoating again. It's complicated. If you want to study Titan lakes, it's a great, there is so much that is not known and so much to try to figure out. It's a great place to dive in.
So we have two on Zoom. One, how wide are these channels? And that was asked about 25 minutes ago, so I'm not quite sure which channels.
Oh, that may have been the, I think it's going to be the Celadon Flumina one. So I do have a scale bar there. I'm trying to remember, I think when I measured it was like maybe 5 to 7 kilometers wide for that channel. And that's probably about like the widest we've got.
Thank you. Next question. Any concerns that a probe landing would contaminate possible life on Titan?
Okay. So funny you should ask that, because I was actually on the review board for the Dragonfly planetary protection. And I don't know when that report is ever going to get published. But yeah, we did worry about that. And there's, so Titan is, I think it was class 2 star in the planetary protection scheme, which means that it's probably not a habitable environment right there at the surface, but we're worried about anything on the surface eventually ending up in the deep ocean. So, can you guarantee, and I remember the number was about 10,000 years. And it's interesting how they come up, so, okay, aside, I learned about how they come up with the numbers of years that you have to worry about protection. And it's based on when do you think people are going to actually end up going there and contaminating it up, right? Because people are kind of filthy. They like to eat, chips and throw them out on the surface and stuff. So for Mars, I believe it's about 100 years. It's either 50 or 100 years that you need to guarantee that you won't have contact between something that was active on the surface and like a habitable environment. And then for Titan, it was about 10,000 years because the assumption was we're not going to be settling on Titan anytime soon. So as long as you keep it clean for the next 10,000 years, you should be okay. And it turns out it's a little bit harder to kind of predict that because you always have the possibility that, it's finite and calculable. You have your probe, which maybe came out of a clean room at JPL, but maybe it was not super clean. And what would happen if you had a meteorite that then punched through the crust and dragged that spacecraft all the way down into the deep ocean? So you have to run through the math and figure out what the probability of that is, and then see if at what level you have to worry about it. And we didn't have to worry about it, but we did have to like kind of calculate it out and figure it out. So the answer is yes, they were worried about it, but no, it's probably not a problem because we were worried about water-based life down in the deep.
All right, so I've got a couple questions for you. Just thinking about life in general, is water really the only kind of substrate that we think, or the scientific community thinks, you can have the chemical reactions of life? Or is it possible whatever fluid that exists can also help conduct those chemical reactions?
So there's going to be, that's a good question. So water is stuff that we're very used to and we understand pretty well. Thinking about different liquids, yes, it's possible that there might be other different liquids and you might have to play some weird games with how you turn your membrane to be able to deal with those liquids and other cellular machinery to do it. The liquid that I would consider being interesting would be maybe supercritical CO2. I think hydrogen sulfide was proposed once. Another one would be actually propane. Propane has a really big liquid range. It's amazing. And it's not super, super bad of a solvent. When we're thinking about Titan and we're thinking about the Titan liquids, methane is an absolutely lousy solvent. That's actually that was most of the work that I did at JPL, was figuring out the solubility of things at Titan, and it's really bad. It's also very, very, very cold. And that is a double whammy because it means that the reactions that you need to do are going to happen really slow, and you can't easily make covalent bonds. You can at best have like maybe a molecular association of things that maybe be oriented but actually not making a covalent hard bond. When we do a lot of our analysis, like for SAM or other types of things, we're looking for materials that are covalent bonds, not chemical associations. So automatically, you're not going to be able to easily detect life on Titan because you're not going to be able to see those molecular constructs very well. And the other whammy is that the stuff doesn't dissolve very well. So one of the things you want to do is you want to catalyze and build things. If you have molecule A and molecule B, you put them together, you make molecule AB, it goes away, you have another thing, A and B come to, and you just you catalyze and you make AB all the time. In Titan, there's a very short list of molecules that are soluble. I can probably give it like 10 or 15 or 20, and that's it. So basically, if you have molecule A and molecule B, you put them together, it's insoluble. It's going to plate right out on your catalyst. You're going to get a catalytic turnover of 1. That's a real problem. So if we're thinking about life in methane, to build a biochemistry will be very, very challenging because you have a very small number of limited molecules that you can actually use to play with it. So there's a lot of issues. So for methane, I don't worry about it so much. Ethane might be a little bit different. Propane would be something that might be interesting. And then you have those other solvents too.
Second question, how long did the Huygens probe last on the surface?
I don't remember. I remember it lasted longer than they thought it would. So the problem with Huygens was that it was sort of dropped off by the Cassini spacecraft, so that you had to worry about, is the Huygens probe going to still be in view of the Cassini as Cassini goes over the horizon of Titan? So that's one of the reasons why they had to design the parachute system, so that they cut the chute and went to a smaller chute so they could get down through the atmosphere as quickly as they wanted to. Huygens was actually an atmospheric probe, not a surface probe. It was designed to sample the atmosphere. Got down to the surface, which was just awesome bonus, but that wasn't the whole science plan.
Thank you.
And once it landed, they did manage to get a little bit more signal from one of the radio telescopes, and it was effectively Huygens was basically transmitting and it was bouncing through the regolith, and they were able to pick it up and actually get a little bit of the regolith profile as well. It was pretty cool. And then it stopped transmitting, which is all good.
And then last question, just Titan in general, is there a hypothesis of, did it form around Jupiter? It could have been captured, I mean, in terms of that. And then because of its distance from Saturn, does the Saturn's magnetic, or basically its gravity, have any kind of impact into kind of squeezing?
Yeah, I don't. So I think I can answer some of it, but not all of it. I don't know the full formation history of Saturn's system. I remember that for Jupiter, it was thought that it formed kind of like a little mini solar system. But Saturn's system seemed to have a different history where things may have formed, but then it looks like something happened and it caused a whole bunch of chaos in Saturn's system and kind of shredded up some of the little smaller moons. I think one of the things I'd heard is that there may have been another Titan sized body, and it kind of migrated and went into Saturn, but caused chaos on its way in. From what I understand, I believe that Titan may have formed pretty much about where it did, and it wasn't very much affected, or at least there's no evident signs on the surface of this chaos. The chaos happened maybe like 1 billion years ago. From the other question was, is there like a much of a tidal flex? So Titan has about a 13-day orbit. That's still reasonably slow. So there's not much tidal flexy energy, which is actually kind of a bad thing because that doesn't make it a great energy driver for life from geophysical activity. And I think there was another part to the question, which was, okay, got it. Awesome.
I assume solar power is not an option for powering any kind of probe on the surface. So what do they use for power?
On the surface, I don't believe so, no. I mean, you could always scale it up to make it really, really, really big. I think one of the things that was, so for Dragonfly, that's going to be nuclear powered. The Aviator aircraft, actually, I think all of these things were nuke powered, if I recall. Let me look. So, sorry about skipping it through. Yeah, so, okay, yeah. So for Aviator, that was going to be an ASRG, that Stirling generator that ended up being a real problem. So that didn't happen. Dragonfly is going to be nuclear powered, and that big thing kind of in its butt there, that is actually the nuclear pack, RTG. The balloon was nuclear powered, and Time was going to be nuclear powered. And having a nuclear powered spacecraft with generating so much heat in a nitrogen chock full mare was going to be an absolute disaster. That thing would have looked like a Pepto-Bismol tablet, just or Alka-Seltzer tablet, just fizzing away. It would not have worked. So that was good that was not selected. But yeah, so thermal management is a problem. But yeah, you have to be nuclear on the surface. For Oceanus, that was an orbiter with a few fly-throughs of the atmosphere. That was going to be fully solar. So you can do that at Saturn. So solar has been proposed for the Enceladus mission as well. So solar is totally cool. Yeah.
Wait.
Oh, sorry.
What type of clothing would a person need to survive on the surface of Titan?
Very warm. So I mean, that's really all it would be. It would be, you have to have very well insulated, but honestly, the pressure is totally fine. And it's nitrogen, it's not corrosive at all. So as long as you were really toasty warm and had a source of oxygen, you'd be fine. Yeah.
Someone would be okay with something like an Arctic parka and then a mask.
It'd be much more. You would have to have a very heavy Arctic parka, and maybe some type of a way to thermally heat yourself. And you would need to effectively seal yourself off, not necessarily, well, because the atmosphere might have a few nasty organics in it, but you would want to prevent any exposed skin whatsoever, because that would just give you instant frostbite. It would be bad. But of all the places in the, I sometimes tell, outreach, little kids, they love this. Of all the places in the solar system, you would last longest on Titan. You could last about as long as you could hold your breath because you'll run out of air. That's what's going to get you. You could probably survive the cold. It won't be fun, but you know, stagger, clap, and then you'd freeze. But for all the other places like Venus would be very bad. I mean, you'd just turn into like, you know, you'd melt, I think. And the moon, you know, yeah. So there's a lot of places where it'd be, but Titan, you could actually survive for as long as you could hold your breath.
Okay, so like a little two-part question.
Okay.
How do we know that the atmosphere, the thick atmosphere, isn't a reason why there's not a lot of craters on there?
Right.
And-
That's an excellent question. And we know that because there's a thing that's called the turn down frequency, where beyond a certain point, your impactors coming in hit the thick layers and they basically just fall apart or then just float down. They don't make a big, huge impact. And we see that on Titan. I'm trying to remember what the number is. I want to say it's maybe like 5 kilometers or something. We don't see craters much smaller than that. So that implies that that's probably the limit for that atmosphere. That help?
And then the other question was, so you notice that like the dunes or the geographical, the geography, the things, the features on the land of Titan is larger, some a bit larger than Earth. So I was thinking about in terms of like how bugs used to be really large on Earth when there's a lot of oxygen. Do you think the atmosphere or something else like that, an abundance of something may help with that, with the features of Titan?
So one of the things that we don't know much about the atmosphere of Titan in terms of its long history. So it depends on who you ask and how they measure. You get kind of like a different answer about how long it must have been there. From the stuff that we did looking at those huge thick piles of organics, you know, at the current production rates, unless something changed a lot and it made a lot of stuff very quickly, we think Titan had to have turned on and had an atmosphere very similar to what it had and just been like boom, pumping out the organics ever since, formation pretty much. There's been some work looking at the isotope ratios. There's some stuff that's called potassium 39, 40. But it's basically a radioactive form of potassium that decays to argon. And argon stays around forever and then it percolates up through the crust and we can measure it. So we know about how much atmosphere might have gone away from being blasted away from the surface, at least recently. And so that suggests that the atmosphere is probably that there's been communication between the deep core and the atmosphere for a very long period of time. What we don't know is if maybe really early, like in the first few 100 million years, that the atmosphere got totally blasted off and that everything has come back. And if I remember, I think to figure that out, you got to use an isotope called xenon 129. And we're hoping that the Dragonfly mission may have a really cool mass spec that might be able to measure some of those isotopic ratios and then figure out that deep, deep history of the atmosphere based on what we see in the isotopes. So a lot of the Dragonfly mission is trying to figure out those very questions, like what happened to the atmosphere and could that have affected how things look? A great question. That's worth a few $billion too, so that's pretty cool.
Anybody else? Hang on line. All right, one more round of applause. Oh,
we got a question.
No, I almost got away with the Audi driver.
You talked a lot about karst. What is karst?
So karst is kind of like dissolution. So it's a place where you have rock that's been kind of dissolved out. And you have like subsurface flow that moves around. And there's actually kind of a cool story. So the Titan karst was actually really useful because we were discovering karst on another world. The Geological Society of America had a karst interest group. And they didn't have a lot of political clout because karst, yeah, whatever, who cares? When we talked to them, they were like, oh, wow, that's cool. That's really cool. We're going to use that. So they ended up saying, hey, look, karst is really important. It's not only important on Earth, but it's also important on other worlds as well. So make us an official division of the Geological Society for America. And they did. And the reason that that's important is because about 30% of the groundwater in the United States is through karst subsurface aquifers, little conduits and stuff in the limestone. And that division's nightmare scenario is that in the Midwest, you have a lot of hog farms. And a lot of those are built on limestone and karst. And if, heaven forbid, there's no regulation, you could have a hog farm penetrate through a karstic conduit and hit the water supply and basically destroy the water supply for a broad region of, say, the Indiana. So by us discovering karst on Titan, we gave the Geologic Society of America and their karst division a little bit more political. They got elevated to an official division of GSA, and we gave them a little bit more political clout so they could then start saying, hey, I think this is an important thing we need to educate the people in the Midwest about. Can you give us some money from GSA? And they said, sure, here you go. And so it's really helped out a lot. It's all good.
All right. Anybody else? All right. How about one more round of applause?
Thank you all much. Cool.